Are you prepared to relinquish everything you assumed you understood about time? To put it concisely, there is no such thing as time, not simply because we say so, but as a consequence of new research findings. But what does this revolutionary hypothesis imply? Why might what we ordinarily understand as time actually be a deception of quantum physics, and what conclusions can we draw from this groundbreaking idea? Albert Einstein once said, "For us physicists, the distinction between past, present, and future is only an illusion, albeit a stubborn one." Abstract time, with its emphasis on now, has no inherent meaning. The more we delve into the subject, the clearer it becomes that what seems so concrete in our everyday lives could not be more enigmatic. While time often represents little more than numbers on a clock or a specific date on a calendar, we typically ignore the question of what time actually is. By definition, though, we are dealing with a physical quantity that describes the arrangement of events in a unique, irreversible sequence, influencing everything, because the universe itself progresses spatially as well as temporally from its beginning in the Big Bang to its end. Thus, time appears to be linear but continues to present us with new mysteries even today. As mentioned earlier, a recent study has concluded that time isn't a fundamental pillar of the universe at all, but merely an illusion that results from quantum entanglement. But what does that mean? Does this imply that there is no beginning or end? Unfortunately, it's not that simple. To understand why time has become the focus of countless scientific discussions, we must first consider the various approaches available to researchers. On one hand, we have Einsteinian physics, which explains large-scale processes in the universe. On the other hand, there's quantum mechanics, dealing with events on a minuscule scale and often appearing to contradict classical physics. Consider Schrodinger's cat, the famous thought experiment published by Erwin Schrödinger in 1935. In this scenario, a cat is locked in a box with a vial of deadly poison, yet no one knows when the poison will release. As a result, the cat can be considered both dead and alive simultaneously. Its state would only resolve to one or the other upon direct observation. But what does a cat in a box have to do with quantum mechanics? Quite simply, quantum mechanics also recognizes a phenomenon called superposition, the superimposition of multiple states. Only when a measurement or observation is made does the system adopt one of the superimposed states. Schrödinger's goal with this thought experiment was to illustrate the contradiction between quantum mechanical and classical physical principles, because a cat cannot be both dead and alive at the same time. In the strange world of quantum entanglement, however, particles in the quantum theory do not have unique states. They instead carry relative probabilities of being in one state or another, only determined upon measurement. Things become even more intriguing when two particles interact because they become entangled, meaning their states are no longer independent of each other but coupled. They become part of a complex probability function that describes both particles as a unified system. To understand this better, imagine an experiment with two entangled electrons. Each electron spin, or intrinsic angular momentum, is measured in two different devices. Ultimately, it turns out that each electron has the opposite spin, which is even more astounding because, according to superposition, their states were not determined at all before the measurement. In other words, the measurement caused one particle to adopt one state and the other to adopt the opposite state instantaneously, regardless of their spatial separation. The two electrons should thus be seen as a unified system. Quantum entanglement also disregards the assumption of locality, which holds that events can only have immediate effects on their direct spatial surroundings. In quantum entanglement, however, entangled particles, even if separated by light years, remain instantaneously connected. The spatially separated particles exchange information immediately or, more precisely, with no delay. It's no wonder that Einstein objected to this so-called spooky action at a distance, as transferring information faster than the speed of light would be required. Even though quantum entanglement often seems incredibly perplexing, it may now offer researchers the opportunity to uncover the true nature of time. Is time simply an illusion? Published in the journal Physical Review, The lead authors of a study from the Italian National Research Council argue that it's possible to reconcile time with both classical laws of physics and quantum mechanics if it is seen as an outcome of entanglement. In quantum mechanics, time represents a fixed phenomenon, an unyielding flow from the past to the present. However, time remains beyond the bizarre and ever-changing quantum systems and can only be understood by observing changes in external units, such as the hands of a clock. According to Einstein's general theory of relativity, time is intertwined with space and can be bent and stretched. Because of this difference between classical and quantum mechanical laws, researchers were at an impasse for a long time. The aforementioned study now suggests that time may only be an illusion resulting from quantum entanglement. But what does that mean? The time problem isn't new in quantum mechanics. The Page-Wooter mechanism, proposed as early as 1983, states that time for an object only emerges through quantum entanglement with another object that acts as a clock. For an unentangled system, there is no time at all, and the system sees the universe as frozen and unchanging. Applying this mechanism to two theoretical quantum states, a vibrating oscillator and a group of tiny magnets acting as a clock, the researchers observed that their system could be described by the Schrödinger equation, which predicts the behavior of quantum objects, all without explicitly using time. The state of the magnets replaced the role of a clock. In the next phase, the researchers repeated their measurements, first with the magnetic clock and then with the oscillator acting as larger objects. Their conditions aligned with classical physics, showing that the flow of time is a result of entanglement even for large-scale objects. In this context, the researchers stressed that the logical path for them is to begin with quantum physics and understand how to derive classical physics from it, not the other way around. Other researchers, however, have been cautious in their statements. Although it's mathematically consistent to envision general time as entanglement between quantum fields and quantum states of 3D space, no one knows if this idea will lead to new or useful insights, such as changes to quantum physics or the general theory of relativity. Yet, suppose we have misunderstood time all along. Could we one day discover attributes currently unimaginable? That is exactly what Michio Kaku was asked during an interview. The famous physicist shared some surprising insights on the nature of time and time travel. Here's what he had to say. Let's start with Isaac Newton. Newton believed that time is like an arrow. Once shot, it moves in a straight line. 1 second on Earth is the same as 1 second on Mars, 1 second on Jupiter, and so on. The arrow never turns. But then along came Einstein, who said, not so fast. Time is like a river, a stream that twists, speeds up, and slows down. What concerns us is this: can the flow of time split? Could it form different branches, or perhaps even loops, winding around itself? If so, time travel becomes something to take very seriously, as Einstein's equations allow for travel through time. For example, enormous rotating cylinders could theoretically let you loop back before you left. Space-time is like a kind of elastic, a trampoline net. If stretched too much, it could tear, possibly forming a shape that would allow us to travel back in time. But there is, as always, a catch: the energy required is immense. Not even a nuclear bomb has enough energy. We would need the power of an exploding star. The question of time travel is riddled with paradoxes. For example, what would happen if we killed our grandfather, thus preventing our own existence? To resolve such thought experiments, one approach is called self-consistency. Even if we aimed a gun at our grandfather, something would prevent us from pulling the trigger. Some hidden physical law would prevent time paradoxes. However, I don't think that's the case. I believe time splits in such situations exactly as we see in Back to the Future. When you alter the past, you create a parallel timeline. Even Stephen Hawking said that there must be some physical law preventing us from going back in time. We've searched for it but found nothing. We know of no physical laws preventing backward time travel. But the energy required is immense, and the civilization that masters it must be extraordinarily advanced. Still, it isn't ruled out. Don't miss our future updates. Like and subscribe to stay tuned. Until next time, we'll see you soon.